Hi there, I'm Mrs. Edwards, and we are going to evaluate some limits as x goes to infinity and negative infinity. We're going to do 11 of them, kind of rapid fire, before we get to some new techniques. So the limit as x goes to infinity of this first rational function. Because the degree of the numerator is smaller than the denominator, we know we have a horizontal asymptote at 0. So the answer is 0 because functions follow horizontal asymptotes at very large and very small values of x. The next one, the degree of the numerator is larger than the denominator, so we do not have a horizontal asymptote, which means that the limit does not exist. If I want to be a little more specific than the limit does not exist and determine whether we are heading to positive infinity or negative infinity as we start substituting numbers that are more and more negative, just substitute one number that is on its way to negative infinity and see if your answer is positive or negative. So if I substitute, let's say, negative 10 into the numerator, I'm going to get out a positive answer. And if I substitute negative 10 into the denominator, I'm going to get a negative answer. A positive divided by a negative is a negative number. And if I substitute negative 100, negative 1,000, I'm going to get an even more negative number. Hence, we're going to negative infinity. This one, the degree of the numerator and denominator are the same, so the horizontal asymptote comes from a fraction of the leading coefficients, which is 5/2. Next, I have a function that is not a rational function because we don't have a polynomial like we did in the first, second, and third example in the numerator and denominator. But the bigger picture, this one is kind of like the first one because the denominator would be getting bigger faster than the numerator. Logarithms get larger very slowly. Exponential functions get larger very quickly. So since the denominator is getting bigger faster, this is going to equal 0. Next, I have 3x squared minus 7x plus the square root of 2. As I start substituting 1, 2, 3, 10, 100, 1,000, the overall answer is just going to keep getting bigger and bigger. So we are not heading to a specific number, and the answers as I continue plugging in larger and larger x's, they're going to be positive. So we're heading to infinity. So the answer is does not exist. All right, here we have one where the limit as x approaches infinity of 2 to the x. 2 to the x, it's kind of like this last one. I plug in 1, 2 to the first, 2 to the third, 2 to the fifth, 2 to the 100, 2 to the million. Our answers are going to get bigger and bigger without bound. So we're not heading to a specific number. We're going to infinity, so the limit does not exist. If I start substituting numbers as x approaches negative infinity, however, so 2 to the negative 1, that's 1/2. If I substitute negative 2, I have 1/4. If I substitute negative 3, I have negative 1/8. Oh, excuse me, not negative, I have 1/8. If I substitute negative 4, I'm going to have 2 to the negative 4, which is 1/16. So our overall answer is getting smaller and smaller and smaller. It's heading to 0. Plugging in negative infinity is really putting that 2 to the x in the denominator. Okay, here we have another one. A little bit tricky again because of that 2 to the power of x. If normally you'd look at it and say, oh, well, the exponential function 2 to the x, that's getting larger much faster than something linear. But because x is approaching negative infinity, let's just focus for a second on the numerator. Substituting in negative 1, negative 2, negative 3, negative 4, that 2 to the x is going to 0, right? Because 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. So the numerator is heading to 0. and then 0 divided by, and then 5 when I substitute in negative numbers going to negative infinity in the denominator. Let's say 5 times negative 1 minus 1, 5 times negative 2 minus 1, 5 times negative a million minus 1. That is getting to be a very, very negative number. So a teeny tiny number in the numerator divided by a very, very negative number, that is heading to 0. The limit as x approaches infinity. We have a trig function, sine x in the numerator, focusing on plugging in larger and larger numbers in for x for sine of x. Our answers are just going to oscillate between 1 and negative 1. So they're going to stay very small, but they're going to change sign. When I substitute in numbers going to infinity into this quadratic, we're going to get a bigger and a bigger and a bigger number. So picture that you are taking a very small number and dividing it by a larger and a larger number. Your overall answer is heading to 0. It's just that your answers are bouncing. To exaggerate that, I'll say my answer could be 10, then it would be negative 10, then it'd be 9, then it'd be negative 9, 8, negative 8. So even though the answers are changing from positive to negative, they are still nearing from both sides, getting closer and closer to 0. The limit as x approaches negative infinity, and we have another exponential, so we need to be careful. When you plug in negative numbers, so negative 10, negative 100, negative 1,000 into e to the negative x, that actually makes the exponent positive. That would be, let's say I plug in negative 10, that would be e to the negative 10, which is e to the 10th, which is 2.7 to the 10th power. That's a huge number. So as we start substituting x values going to negative infinity, that numerator is getting huge. And then the denominator, as I substitute in negative numbers like negative 10, negative 100, negative 1,000, x plus 1 is going to be getting to be more and more negative, but slowly. So the numerator is getting larger fast, the denominator not so fast. So it's going to go to infinity. And because when I substitute in negative numbers in the numerator, I get out a positive answer. And when I substitute in negative numbers, big numbers into the very negative numbers into the denominator, I'm going to get a negative. Positive divided by a negative, we know we're heading to negative infinity. The limit as x goes to infinity of sine of x. Our answers are going to go, as we substitute 10, 100, 1,000, 1,001, 1,002, our answers are going to oscillate between 1 and negative 1, but we are never going to get any closer. We're going to go 1, negative 1, 1, negative 1. So we're not narrowing into a single number. We just keep that same distance. So it does not exist because it's oscillating the same distance back and forth. Introducing a few limit properties, we are given the answer to the limit as x approaches c of f of x and the answer to the limit as x approaches c of g of x. In part A, notice that f of x is being cubed, and we want to find the limit as x approaches c of the function being cubed. Well, one of the properties is that you can find the limit as x approaches the function first, and then after the fact, cube your answer. So I'm going to find the limit as x approaches c of f of x, which we already have the answer, so that's 3, and then I'm going to cube it after the fact, and our answer is 27. All right, part B. If you're finding the limit of x approaches c of a few functions that are added or subtracted, well, you can pull those apart and you can find the limit as x approaches c of each of these functions separately, and then at the end add those answers back together. If I find these limits separately And now I know the limit as x approaches c of f of x was given, that was 3, and the limit as x approaches c of g of x equaled 2. So 3 plus 2 is 5. Part C, we have two functions that are being multiplied together. So you can pull this limit apart and find the limit of each function separately and then multiply the answers together. So the limit as x approaches c of f of x is 3, and the limit as x approaches c of g of x is 2. So the answer to the limit as x approaches c of f of x times g of x is 6. We can do the same thing with dividing fractions. If you have a function where we have two pieces that are being divided, well, we can find the limit of them separately and then divide those answers. So in this case, that would end up being 3 over 2. If we use the properties of limits, in this first example, we could pull apart the addition here, 3 over x plus 2, and find the limit of each one separately and then put them back together. So the limit as x goes to infinity of 3 over x, that means we're dividing by the 3 by a larger and a larger number, so the overall answer is going to go to 0. In the second piece, the limit as x goes to infinity of 2, well, if your function is just y equals 2, it's a horizontal line at 2, so the intended height everywhere is 2. You plug in 10, 100, 1,000, and you're substituting it into 2. There's no place that you can put that x, so the answer is always 2. So the limit as x goes to infinity is 2. Both of these are real numbers, and so we add those together, and the limit of the overall function 3x plus 2 is 2. A warning if you're using these properties. If you pull things apart and then at the end you're going to put them back together, you want to make sure that you don't have any indeterminate forms. If you come across indeterminate forms, then these properties do not apply. Some examples of indeterminate forms. If you have infinity plus a number, that does not equal infinity. That is an indeterminate form, and you cannot use this method. If I had 0 over 0, again, indeterminate form, so you would not be able to use these properties. And I'm trying to think of another example, like infinity divided by infinity, a number to a power of infinity, any of those indeterminate forms. Okay, so here's an example of that happening. We separate, and then when I find the limit as x goes to infinity of 3 over x, 3 divided by a larger and larger number heads to 0. And then in the second limit, the limit as x goes to infinity of x over 5, if we take a larger and larger number dividing it by 5 every time, the overall answer is getting bigger and bigger. So we are heading to infinity. This becomes 0 plus infinity. That's one of those indeterminate forms that I'm talking about. This is inconclusive. So what we can do is we can rewrite the original problem, instead of as two separate fractions, we can rewrite it as a single fraction by finding a common denominator. So let's multiply the numerator and denominator here by 5 and the numerator and denominator here by x so that we have a common denominator. Now that we have a common denominator, we can combine. Now we're back to those rules where if we just know which the numerator or denominator is getting bigger faster, we can make our decision. Okay, so in this case, we have a quadratic on the top and something linear on the bottom. So the numerator is getting larger faster than the denominator. So the answer is going to be does not exist. It is a coincidence. I know some of you are thinking, well, 0 plus infinity is infinity. No, every time if you get a number plus infinity, that does not equal infinity. All right, so let's take a look at this example. Sorry, the 9 over 25 is coming too soon. We have a lot going on here. these rules are really nice to be able to pull it apart into some smaller, easier problems to work with. So I'm going to begin, because I have this purple piece times the blue piece, I'm going to pull that apart as two separate limits. Okay, a couple other things going on here is cosine of 1 over x divided by 5. Well, dividing by 5 is the same thing as multiplying by 1/5. So 1/5 would be a constant multiplier, and I could just move that out front. So notice I have 1/5 multiplied by the cosine of 1 over x. Another thing that I can do is this 3x over 5x plus 4 is to the second power. And so we know that we could find the limit of just that, 3x over 5x plus 4. And after we find the limit, then we square it. So I rewrote it here with the 1/5 out front of the limit, and then here finding the limit and squaring it after the fact. All right, let's look at each piece. So 1/5 is going to be 1/5. The limit as x goes to negative infinity. So 1 divided by -1, 1 divided by -10, 1 divided by -100, 1 divided by -1,000. What's inside parentheses here is going to 0. So we're getting closer and closer to whatever the cosine of 0 is. Well, the cosine of 0 equals 1. Right, then multiply, and then on to this one. The limit as x goes to negative infinity. 3x over 5x plus 4, they're getting larger at the same rate. They're both linear. So we're going to have a horizontal asymptote at 3/5. So the answer to this one would be 3/5, and we can square it after the fact. And so if we take 1/5 times 1, we get a fifth, times 3/5 times 3/5, and we get 9 over 25. And that's our final answer. But hopefully you can see the rules in action here. Again, I pulled apart multiplication, and then the divide by 1/5 was times a fifth, so I was able to take out a constant multiplier. We had a fraction to an exponent, so I could find the limit of just the fraction, and after the fact apply the exponent. Try to pick one that kind of had all of the rules in there. Let's run through a couple more. This one here, in disguise a little bit, we have kind of the square root of x over the square root of x. Hopefully you can see that it is getting larger at the same rate, the numerator and denominator. And we're going to kind of look at a shortcut here in a second, at least in my mind. But let's look at it purely algebraically for a moment. If you have a square root of a fraction, then that's equivalent to the square root of the numerator over the square root of the denominator. So I'm going to undo that and have the square root of a single fraction. Now technically here, right, a square root is the same thing as to the power of 1/2. So if this is to the power of 1/2, then that exponent, using those rules, we can find the limit as x goes to infinity of the fraction, and then after the fact, apply the exponent 1/2. So the limit as x goes to infinity of something where the degree of the numerator and denominator are the same is going to be a fraction of the leading coefficient. So it's going to equal 5/3. And then this whole limit equals 5/3. It's still going to be to the power of 1/2, which really means the square root of. So if you have the square root of 5 over 3, that's like the square root of 5 over the square root of 3. Rationalizing that denominator by multiplying the top and bottom by root 3, we're going to have root 15 over 3. I feel like you can skip a lot of these steps because the part that is really contributing to how fast this is growing, it's not the -2 and it's not the +4, because at enormous numbers, substituting in a billion and subtracting off 2, that -2 is insignificant. So the main thing here is the square root of 5x over the square root of 3x. And the coefficient in front of the square root of x would be the square root of 5, and in front of the square root of x in the denominator would be root 3. So I personally can look at this original function and go directly to root 5 over root 3. I'm hoping you can see that, but otherwise you can just apply the algebra and you'll be fine. Here's another one where the degree of the numerator and denominator, at first glance, you may not see they're the same. But if we just ignore this plus 2, kind of using that technique, and the minus 3, these ones are not going to be significant at enormous values. They're negative a million, negative a billion. So we're going to focus on the square root of 3x squared over 5x. The square root of x squared is just x. And so the degree of the numerator and denominator are the same, but the leading coefficient here would be root 3, and in the denominator it would just be 5. So root 3, and then notice I have a negative 5. Especially when you're going to negative infinity, you should substitute at least a number towards negative infinity to verify your sign. If I substitute in the numerator, say negative 10, then this is going to be positive in the numerator. But if you plug in negative 10 in the denominator, you're going to get a negative number. So as we start to substitute in numbers that are more and more negative, the answers we get out, they're going to be negative. So root 3 over negative 5, not positive 5. All right, so one more of that type. Looking at the numerator versus the denominator. The 2x minus 1 and the minus 3, yes, it is contributing to the size of the numerator and denominator, but at enormous values, what is really making the biggest difference is the cube root of 8x to the third and the minus 5x. That's our focus. And after that, if you just focus on that, the cube root of x cubed is x. So see how the degree of the numerator and denominator are really the same, just kind of disguised. So the leading coefficient, it is not 8. We want what is the leading coefficient on x to the first power. Well, the cube root of 8 is 2. And then so this would be 2 over negative 5. Now, let's just double check on the signs one more time. Because anytime we're heading to negative infinity, we want to especially be careful of the sign. So let's just substitute any number that is heading towards negative infinity to check on the sign. Let's pick negative 10. If I substituted in negative 10, 8 times negative 10 times negative 10 times negative 10 is a negative number. The cube root of a negative number is negative, so that's why this is negative 2. The 2 is the leading coefficient, cube root of 8, but negative. Okay, and then if I substitute negative 10 in the denominator, or even just in this little piece, notice the overall answer is going to be a positive. So it's a positive 5. I tried to pick this example because at a quick glance, you would maybe think that you had the right answer because you were thinking cube root of 8 is 2, and then over negative 5, and you would have gotten negative 2/5, but not necessarily for the right reason. So anytime your x is going to negative infinity, make a substitution just to verify if you are going to a positive or a negative version of the number. You can check yourself. Negative 2/5 is negative 0.4, and if I did have a calculator, I might just substitute in negative 1,000 into this entire expression, and I'm going to get a number that is very close to negative 0.4, because that is the number we're getting close to as we choose x's heading to negative infinity. There are a handful of limits that are considered limits that you just memorize, and these 5 are those limits. So you want to write these ones down. All right, you have that copied down? You can pause it if you need to. The first 2 here I think are very intuitive, because if you substitute in 10, 100, 1,000, numbers heading to infinity, 1 divided by 10 is 0.1. 1 divided by 100 is 0.01. 1 divided by 1,000, 0.001. The overall answer is heading to 0 because it keeps getting smaller. Also here, 1 over x. If I plug in negative 10, 1 divided by negative 10 is negative 0.1, 1 divided by negative 100 is negative 0.01, and so on. So the answers are getting smaller, 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 and we're heading to 0. This one is less intuitive, and that's why it's memorized. Okay, the 2 down here, usually you see sine x over x and 1 minus cosine x over x often enough that hopefully they start to jump off the page at you and you're like, oh yeah, that's one of those memorized ones. But sometimes you just forget which one's which. Is that the one that equals 1 or is that the one that equals 0? So just a silly observation to help your memory. The word sine, S-I-N, the I is kind of like a straight line, that's the one that equals 1. And then the one that has cosine in it, that's the one that equals 0. Sometimes you will see these 2 memorized ones here at the bottom. They're in there, but they're a little bit disguised. Okay, so I'm going to show you an example of what I mean. Here we have the limit as x approaches 0 of sine of 4x over x. You cannot factor the 4 out. Oh my gosh, please don't do that. That is an atrocity. Danger. Whenever you're dealing with trig functions or logarithms and you have something in parentheses, there is no such thing as distributing through that or factoring out. No. Okay, so that 4x there, that's like a brick. You are not going to be able to do anything about that one. But the property that is the memorized property here, you see the x's, but they don't represent the same thing. Let's look at it maybe a little differently and say sine of something over the exact same something. We want to force this to look like the sine of something over the exact same something. Since I can't do anything about this 4x, I want there to be a 4 right there. Now, as silly as this sounds, we're just going to put it there. No, we can always multiply by another name for 1. So I'm going to multiply the numerator and denominator by 4. If I do multiply the numerator and denominator by 4, well, the denominator would be 4 times x, so 4x. Now the numerator is 4 times the sine of 4x. The 4 in the numerator we can think of as a constant multiplier because I don't really want it there. So I'm going to take the 4 that's here and throw it out front using that property of constant multipliers. Those can go out in front of the limit, but the 4 here, I'm going to put it with the denominator. Now look, we have the sine of star over star. In other words, the sine of something over the exact same something. That's what we have created. So the limit as x approaches 0 of sine of 4x over 4x, sine, that's the one that equals 1. So there's our 1 and that 4 out front. So we have 4 multiplied by 1 and our answer is 4. Evaluating the limit as x goes to 0 of 1 minus cosine x over 5x, that really resembles our memorized limit. But remember, in the memorized limit, it's really saying 1 minus the cosine of something over the exact same something. Currently, we have an x and a 5x, but we need those to be identical. To do that, I'm going to rewrite this limit. All right, so I'm going to rewrite that. And notice I have 1/5 multiplied by 1 minus cosine x over x. When you have a fraction times a fraction, we have a numerator times a numerator, and that would take us right back to, there. And if I took 5 times x, I would be right back there. So these two are equivalent. But what I've done is I have emphasized that 1/5 is a constant multiplier. We have some limit rules, and if we're multiplying by a constant, our rules say that we can move that constant out front, evaluate the limit, and then multiply it back together. Rewriting it with 1/5 out front, it looks like this. The answer to the limit as x goes to 0 of 1 minus cosine x over x is our memorized limit, so that equals 0. And 1/5 multiplied by 0 is 0.